1969, researchers transmitted the first message over the ARPANET, the precursor to the internet. The message they sent consisted of two characters, L and O. They wanted to transmit login, but the system crashed and they only got the first two characters out. So a few years ago, I experienced something that I thought was a pretty significant advance. It's not nearly as significant as the telephone or the internet, nowhere near that, but it was significant to me because it illustrated a sign of what might be to come in the world of robotics. And that was the first robotic foundation model API call over the internet. The robot was located at UC Berkeley, and the command that my student Kevin Black sent was put the eggplant in the pot. And there was a foundation model that was actually running on a remote server in Mountain View, running a model that Kevin didn't really know how it worked, and he was able to send the robot did the task, something that any person could do. But Kevin had been working on this problem for quite a while, and he was actually pretty impressed by it. He said it's unstoppable compared to the kinds of systems that have been developed with smaller models. And this was the RT2X cross-embodiment VLA. I don't think it's the same as the telephone or the internet, but I think it's a sign of things to come. And I think as we develop robotic foundation models that can be called remotely over APIs over the internet, enough power to enable any robot, and perhaps this will be seen as a very early first step towards that. Okay, so what's a robotic foundation model? Arguably the first vision language action model, which is what today we refer to as robotic foundation models, was RT2. And RT2 was actually a very simple model. It was based on large language models that were adapted for processing images, and then further trained to perform robotic control. So vision language models, they basically process things like visual question answering. You can show them a picture, ask a question, and the model will try to respond to that question. To adapt them to robotic control, we simply pose a robotic control problem as a question, and the answer to that question is the motor commands that should be sent to the robot. RT2 was based on a model called PolyX, which back then was a fairly sophisticated vision language action model, and it could perform a variety of rudimentary language commands. To fully unlock the power of robotic foundation models, we need a little bit more. We also need the right data sets. And step towards this that I think was quite significant was the development of the RTX data set. The RTX data set was a cross-embodiment data set that contained data from many different kinds of robots and was specifically intended for training robotic foundation models of this sort. RTX consisted of data from 34 different research labs, 22 different robot types. But rather than going through all the statistics, I think it's maybe easiest if I just show you some of the clips in this data set. So you can see a wide variety of different arms, a wide variety of different settings, and a wide variety of different tasks. So now this is a data set that has the beginnings of that diversity and variability that we need to train robotic foundation models. One of the really interesting things that we saw with RTX was that a generalist model trained on this cross-embodiment data set could actually outperform more specialist, specifically adapted to individual settings. So after we trained we sent a subset of the labs that had contributed data and asked them to evaluate the model against whatever technique they were developing in their own domain. So the RTX result is shown by the rainbow-colored bar. It's a different task in each of the labs, and then the leftmost bar is whatever method each lab was developing. And on average, the cross-embodiment model was about 50% better than the model that had been developed individually in each of these labs. So that's pretty exciting because each lab was developing whatever model worked best for their setting, and this cross-embodiment model that included data from all these other robots actually outperformed it. So that's kind of the beginnings of that benefit of generality that we've come to expect in other domains like natural language processing and computer vision. RT2X was also more effective at following language instructions even for the most overrepresented robot, which was the Google robot, where it could follow a variety of different commands. For out-of-distribution commands, it was about 3 times better than a model trained only on data from this single robot. But RT2 was really a first-generation VLA. It was designed simply by framing the robotic control problem as a question answering problem, which is a pretty simple way to do this. Now we have much better VLAs that are much more able to handle complex and dexterous tasks. So let me tell you a little bit about how VLAs are designed. First, let's start with language models. A language model, as most of you probably know, is a large transformer that predicts future tokens in text. To adapt large language models to also accommodate images, we can embed images into the same embedding space as text, and we get a vision language model. First generation VLAs were trained by simply taking vision language models and replacing the suffix with a robotic command represented as discrete tokens. So the architecture for first generation VLAs was exactly identical to the architecture for standard VLMs. Second generation VLA models embrace the fact that actions are not discrete tokens, but actions are continuous. And second generation VLAs use some sort of continuous action distribution, typically represented by a high capacity multimodal model such as a diffusion model or a flow matching model that can tap into the internal representations of the base VLM, but can produce continuous actions, typically as temporally extended action chunks, which means that they produce multiple steps of future actions at the same time, which leads to significantly better performance. Now, there are a variety of different ways to design second generation VLAs, but what they all have in common is that they use a separate generation mechanism more adapted to continuous actions, typically for higher frequency and more dexterous control. So they add a dedicated continuous output mechanism that can specialize for motor control as like a kind of virtual motor cortex. So the second generation VLA that I want to tell you about is called Pi0, which was developed at Physical Intelligence. Pi0 is based on the 3 billion parameter polygemma VLM, which is then augmented with an action expert. So in the same way that you can have a mixture of experts model where different weights are used to generate outputs for different tokens, in the Pi0 VLA, there is a separate action expert that's actually quite a bit smaller than the base VLM that is dedicated to producing continuous action chunks using flow matching. So the Pi0 second generation VLA takes as input between 1 and 3 images, depending on the embodiment of the language command. The action expert attends to all of the internal activations in the base LLM. It also processes continuous information like joint angles and outputs an action chunk of 50 time steps with a high enough dimensionality to control the data set. So for this because it can allow us to represent very complex multimodal distributions. Now, of course, the Pi0 model is only a small part of the entire robotic foundation model. The other part, the data set. Pi0, we data set of about 1,000 hours of data from over and combine previous, such as the data set used in RTX. New tasks, make a box and fold it so that it's fully assembled. Here, Suraj places the box in front of the robot and it gets to work. This is a robot that's very similar to the Aloha Trosson setup, but the model can control a variety of other robots as well. And this is a very difficult task. It requires a lot of dexterity. It requires the robot to use the table surface to support the box as it folds it and to apply force correctly at the right time and in the right place. The policy is far from perfect, so it'll sometimes make mistakes and have to retry, but it does fold the box successfully in a variety of locations. We evaluated the benefit of using a pre-trained model quantitatively. So here, the solid bar shows the performance of the model after pre-training on the large diverse cross-embodiment data set and then fine-tuning on each of these 3 tasks. The striped bar shows the performance when only training on the target task. And you can see that on 2 out of these 3 tasks, we get a very large improvement from pre-training. Now, Pi0 can also perform very complex tasks. One of the more complex tasks we evaluated on was folding laundry, and it can fairly reliably fold various clothing items, including shorts, t-shirts, and so on. It can do so in a variety of settings. It can also do so with different robots. So the second robot here is actually a mobile robot. You can see it makes some mistakes, but eventually recovers and folds the clothing correctly. And it can also do other clothing-related tasks like taking laundry out of a dryer. One of the really exciting things about training a model like this on large amounts of data is that it absorbs a lot of knowledge from pre-training, which means that it can recover from perturbations. So here, Michael places another clothing item on the table, and then the model simply puts it away and then continues with the task. These videos have more perturbations. You can see in some of them, Michael places an additional clothing item on the table or messes with the item as the robot is folding it, and in all these cases, it eventually recovers. And we can actually combine multiple different tasks into one temporally extended execution. So here the robot is performing a full laundry folding task where it takes laundry out of the dryer, brings it to the folding table, and then folds all of the clothing items in sequence. Now, since developing Pi0, we've actually made quite a number of advances, and our most recent revision, which we call Pi05, actually incorporates a number of other capabilities. Pi05 is really designed around the goal of generalization to very long horizon tasks in entirely new settings. So what you're seeing here is an evaluation of Pi05 cleaning up a bedroom. This bedroom was never seen in the training set, so we brought the robot into an entirely new home and tasked it with cleaning the bedroom, putting away the clothing on the floor, putting away the trash, and making the bed. Now, to enable Pi05 to perform such long horizon tasks, there are a number of additional innovations that we developed. One of them is the ability to perform both high-level and low-level reasoning. So unlike Pi0, which directly takes in a command and outputs actions, Pi05 takes in a high-level command like clean the bedroom, and then performs a high-level reasoning step where it selects an appropriate sub-step to perform for the current point in task execution, like picking up the pillow. It passes this low-level command to the rest of the model, which then actually selects appropriate actions. And this is very important if you want complex long horizon tasks. And it's also a more effective way to transfer knowledge from web scale pre-training, because inferring these semantic steps is something that the base VLM should be quite good at. We used a very complex task mixture for Pi05, which included data from many different robots. And we employed a mixture of training objectives, including training on question answering problems, bounding box detection problems, and of course the robotic tasks like predicting semantic substeps and of course predicting actions. This is a summary of the pre-training and post-training data for Pi05. I won't go into detail about all of this, but one thing I want to point out is that data for mobile manipulation comprised only 3% of the Pi05 training set. This data is quite difficult to get. These are complex robots. And actually, the overwhelming majority of the data, 97% of it, came from other robotic embodiments, including much simpler robotic arms that we could place in a variety of different locations, robotic data collected in the lab, and so forth. So the fact that this model can generalize so broadly in real-world settings, while only having 3% of its data set come from mobile manipulators, I think is actually pretty interesting. Here are some more demonstrations of Pi05 in a variety of settings, performing a variety of tasks. You can see that it's doing things like folding towels in real kitchens. In the bottom left there, you can see Quan, one of the researchers, is perturbing the robot in various ways as it tries to clean the bedroom. In the lower right, you can see that it's cleaning up a kitchen and so forth. And all of these experiments are in settings that were not seen in the training data, so these are entirely new homes. So a few takeaways from this discussion. What do we have so far? We have a prototype of a generalist model trained on many different robots and a VLA recipe that is suitable for dexterity and fluent robotic control. It achieves excellent performance across a range of very complex tasks, but there are still some things that are lacking. One thing that is lacking is that this model is trained entirely with imitation. It's not really directly optimizing for task success, robustness, and speed. And one of the things I want to talk about in the last portion of this talk, which is a little bit more forward-looking, is the kind of reinforcement learning technologies that are on the horizon that we could incorporate into VLA models in the future to greatly boost their robustness and performance. So to use an analogy, when we train standard foundation models, LLMs and VLMs, typically we do so in two stages. We have a pre-training stage where we collect large amounts of data from the web, and the purpose of this stage is not really to get the model that really performs tasks, but rather to just bake a lot of knowledge into the model. So this is the pre-training stage. And then we have a post-training or alignment stage where we would use either high-quality SFT data sets or some sort of reinforcement learning, not necessarily to gain new knowledge, but specifically to teach the model how to perform tasks that the users actually want and how to perform them robustly and effectively. And I think in robotic foundation models, we'll see the same separation where we'll have pre-training phases and a post-training or alignment phase, where in the post-training phase, the goal will be to use things like reinforcement learning and high-quality data to get the model to perform a task really well. So, apologies, let me restart the video here. There we go. So, what you're seeing here is a reinforcement learning process that is training a robot to insert a chip into a PCB board. This is not a VLA, this is a single task reinforcement learning procedure, but it is a very efficient single task reinforcement learning procedure. And one of the things that we figured out how to do over the last few years is get real-world reinforcement learning to be extremely efficient. So the base algorithm for this system is called RLPD, RL with prior data, although a variety of algorithms could be used. It's an off-policy active critic method initialized from demonstrations. The observations consist of raw images from a wrist camera. It's very important to use a pre-trained vision encoder, but otherwise it's a fairly standard setup. And the reward consists of an image classifier that simply classifies whether the robot succeeded or failed at the task. So it's a very sparse reward. Optionally, we can incorporate human interventions into this system, such that when the robot fails, a person can intervene and suggest a correction, which both provides an additional reward signal and additional data. Here is a video of that in action. So when the frame is highlighted in blue, the robot is performing the task autonomously. When it's highlighted in red, there's a user that gives an intervention. And these interventions during training can actually make the learning process a lot more efficient. It's like a teacher who coaches the robot through how to perform the task while still letting it attempt the task on its own as well. So this complete system, which we call SERL, turns out to be very effective at learning a wide variety of individual tasks. So whereas the VLA is a kind of generalist, the SERL RL system is really a system for training specialists. But it can be used to train very good specialists for a wide range of tasks. These tasks include putting the timing belt on the gears, assembling furniture, flipping an egg, highly dynamic tasks like whipping the Jenga block. So these are fairly complex tasks to learn. The robot can learn them to a very high degree of effectiveness. And it's a very complementary kind of capability to the VLA. The VLA is a generalist. The RL system is a highly skilled specialist. And of course, what we would really like to do is put them together so that the specialists can supervise the generalist to become a better generalist. So the specialists are very effective. This is an example of perturbation robustness. So here, Charles, one of the authors on this paper, is perturbing the robot as it puts the timing belt on the gears, and you can see that the robot recovers quite proficiently. Combining these specialists into a generalist is still an open problem. We've taken some initial steps towards solving it. One of these steps is a method that we call RLDG, which directly uses specialized RL algorithms to generate training data for training VLAs. This kind of research, I think, is still in its early stages, but I think it's extremely promising. In our prototype for our RLDG, we were able to train specialist policies for inserting a variety of connectors, VGA connectors, USB connectors, and so on. And then after we train a VLA on data from these specialized RL methods, that VLA can actually generalize to entirely new connectors. Now, of course, this is much more narrow than the kind of cloth folding and box building and generalist capabilities that I showed before. So it's an early step, but I think in the future we'll see a lot of progress in combining reinforcement learning with VLAs, and that might lead to much more reliable and much more performant systems. So to conclude, what we have so far is some very efficient RL algorithms, a way to distill RL skills into VLAs, but there are still open problems. We still don't have a stable, effective, and reliable end-to-end training procedure for VLAs with RL. I think there's a lot more we can do in terms of boosting exploration and improvisation with VLAs to actually aid the RL process. And I think there's a lot of system building to be done here. So I'll leave you with these thoughts and stop there. Thank you very much for listening.
谢谢，非常感谢 Professor Levine 给我们。